kiddos, in our last video we talked about acidity and we looked at how we can determine between two compounds which one might be more acidic. And if you remember, the way that we did that is we talked about quantitative values. We talked about pKa values, and we said that, hey, if something has a lower pKa value than another compound, then that means it's going to be more acidic. We related that then to which side of an equilibrium expression that might favor. So is it going to favor products? Is it going to favor reactants? And all of that was sort of determined when we looked at our conjugate acid-base pairs. It was all sort of determined by a numerical value, a quantitative value, which was the pKa. In today's video, we're going to talk about how we would do that for qualitative things, meaning that what if we didn't have the numbers? What if we didn't have the pKa values and maybe they weren't readily available? What would we do then? And so the way that we would do that is that we would look at the two things that we had, or more, but in general, we're going to be comparing two. And we would walk through this process, this acronym here, of 4 different ways that we can look at a structure and be able to determine something about its acidity from that. And remember, what we're almost always looking at is what sort of structure is going to be more stable once we remove the hydrogen, because that's what's happening in acidity, is that a hydrogen, a proton is being donated somewhere. And so what left over, what conjugate then, is going to be a more stable situation. And so we're going to talk about these acronyms. Remember that as with everything in chemistry, this is, I don't want to say a partial truth, but this is the truth, but there are exceptions just like there are almost everything. So let's start with the first one. So the first one is, the first word in the acronym is atom. And the atom matters in this way. Okay, if things are in the same row, then electronegativity matters. Okay? And if things are in the same group, okay, meaning column, okay, so row on the periodic table, column in the periodic table. If they're in the same group, then size is what matters. So let's draw a quick little miniature part of the periodic table there. So noble gases, obviously we're not real worried about those. Group 2 obviously is where we're pretty worried about things. And so we've got fluorine, we've got oxygen, nitrogen, and carbon tends to be where we are really concerned with. We could draw a couple of things over here in the next group too, because occasionally some of these things will jump into our organic things as well. Phosphorus, definitely sulfur, and of course some chlorine. Those halogens are always important. So what does that mean? So that means that in the same row, electronegativity is what matters the most and what is going to make something more stable. And so in the case, if we look here, if it would be much more advantageous for us to pull off a hydrogen off of an oxygen than it would be off of a carbon. Okay, why is that? Well, because oxygen's a lot more electronegative. It's a lot more able to absorb that lone pair that's going to come from the hydrogen as the proton is donated. Okay, and so electronegativity matters most there. And we'll see examples here in a second. So that's electronegativity in the same row. In the same group, so if we were comparing, say, oxygen and sulfur, then what matters most there is the size, okay? And the bigger it is, the more stable it's going to be once it loses that hydrogen. It's got a lot more room to absorb those extra electrons and have space for those electrons. And so that means if we're going down a column, then size matters. And if we're going across a row, it's electronegativity that matters. And in both of those cases, the higher value is what makes it more stable and more acidic for what we're talking about. So let's look at a couple of examples of that real quick. Okay, so here are examples for the atom thing. In each case, like in this case, obviously there's a hydrogen that we pointed out. We're trying to see which case is more advantageous to remove a hydrogen. Well, in this case, we're comparing a hydrogen connected to a carbon to a hydrogen connected to an oxygen. Carbon and oxygen are both in row 2 of the periodic table. Oxygen is obviously going to be a lot more electronegative. And so what that means for us is that it is going to be much more stable if we remove this, because if we remove that and add those in there, that oxygen is a lot more able and capable, because of its electronegativity, much more stable if we add a lone pair to it, okay, than compared to the carbon. More electronegative, wants those electrons there, makes a lot more sense, and therefore this is going to be our more acidic atom. In the case of oxygen and sulfur, and again you see two very similar compounds, water and dihydrogen sulfide. And so what's the difference there? Well, they're not in the same row, but instead they're in the same column, the same group of the periodic table. Sulfur being in row 3 there, the next row down from oxygen, is going to have an extra energy level. Therefore, it's going to be bigger. By virtue of it being bigger, it's much more able to absorb, again, that extra pair of electrons there. And it's going to be much more stable and capable of handling that extra charge that's going to be there. Because remember, when this happens, what's going on? Well, now we're going to have a negative formal charge on that, right? And so the sulfur is going to be very capable of absorbing that because of its extra size. A lot more room in the electron cloud in that case. So that's the atom part. Let's move on to the second of our letters in our ARIO. Okay, so the second of our letters in ARIO is resonance. We got 2 structures here. And what resonance means is that if we have resonant structures, then that is going to make this structure generally more stable, because what resonance tends to mean for us is that we're going to be able to delocalize some electrons. And what that means is that whatever formal charge is going to be left once the hydrogen leaves is going to be able to be stabilized by being a resonant structure. So that formal charge is essentially spread out over a delocalized area, whereas it would not be if there was no possibility of having resonance. And so if you look at our 2 examples here, okay, so we have an ethyl alcohol here, and we have what is acetic acid, which sort of is a dead giveaway. But let's look at why that would be the case. So if I remove my hydrogen, okay, so then I get that lone pair there and a negative charge. Okay, we get rid of that hydrogen. We're going to do the same thing down here. Okay, I moved that in, and I've now got an extra one there. So the difference between these 2 structures after we do that movement is that this negative charge here is able to be moved via resonance to different locations. And so I could draw a resonant structure here where I could say, okay, well, what about if I move that there and then move that up there? And so therefore I've got a resonant structure, okay, where I've got my negative charge there. Okay, in that particular case. And so what that means is that that negative charge is now stabilized by that delocalization, by that resonant structure, by the fact that that area of electron density is being shared amongst those 3 atoms, whereas in this case there's really no chance for that to happen. There's no resonance there. There's no real way that we can make that go that will share that charge anywhere. So the more resonant case then is going to be the one that's more acidic, the one that has more possibilities for resonance, or we could say for stabilization of the charge through delocalization. Okay, so our third letter, I, stands for induction. And induction essentially means how is the pull of electronegativity on, not on the atom that the hydrogen is connected to, but on some atoms further down the line in the chain, and not too far down the line, or they're not really going to have much effect, but a little bit down the chain, because we get inductive effects because the electronegativity of those other atoms will start to pull the cloud. Remember that if we're talking about a molecular orbital sort of idea here, where it's not just like each individual atom has electrons that are connected to it, localized in other words, but instead that there's a molecular orbital, there's a cloud around the whole molecule, then the electronegative atoms have this inductive effect where they're pulling the cloud a little bit more towards themselves. And what that allows is that it makes it a little bit easier then for that hydrogen then to break away. And so that's going to mean that it's a more acidic case. What you'll see here is that we're sort of cascading in the way that we work. If we looked at these 2 structures, well, they both got the hydrogen attached to the same atom, so that doesn't help. Both of these structures can have resonance, and so that doesn't help. They're both the same essential resonance structure. And so we get to an inductive effect, and we see that there's all hydrogens at the end here, not electronegative at all. But at the end of this molecule, there's a chlorine, and so that chlorine is going to pull that over a little bit, and therefore it's going to mean that this hydrogen is a little bit more, or even a lot more acidic than this one. You may remember from your other chemistry classes that obviously the more atoms that we put down here, the greater that inductive effect, and the more acidic it makes it, the easier it makes it to pull away. Oxyacids are a really good example of that if you remember your college chem or AP chem stuff, where as you had more oxygens attached to the ends down here, that inductive effect makes it easier and easier to pull that away. And so I always like to tell my students about, or to explain about the chlorates and the chloric acid series, because you've got weak acids, hypochlorous acid, super weak. You've got chloric acid, and that's not terribly strong either. But then you get to perchloric acid, where you've got 3 oxygens down here on the end, and that is a really powerful inductive effect, makes it really easy to pull that off. And therefore, the more electronegative elements you have, not directly attached to the hydrogen you're trying to remove, but a few spaces down the line, that's going to have a powerful effect and make it more acidic. So that's our third letter. And now for our last one. All right, so let's talk about a situation where nothing of the first three really explains it, where the atoms, it's these hydrogens, so I'm going to talk about two hydrogens on the same molecule here. So the atoms are the same, they're both connected to a hydrogen. There's a capability of resonance in each of these structures. We've got double and triple bonds here. There's no real inductive effects. I don't have anything really electronegative anywhere on this atom. So that brings us to our fourth letter, which is orbitals. And the orbitals comes down to this. The more hybridization there is in the structure or in that area where you're pulling the hydrogen off of, the more stable it's going to be, and therefore that's going to lead to that being the more acidic particular case. So if we look at these two structures and we talked about what is our hybridization here? Well, this is sp and this is sp2. Sp bonds are going to be much shorter, okay? And so since those are much shorter, then that means that the electrons that are left are going to be therefore much closer to the nucleus, and therefore it's going to be a much more stable structure. And therefore, if we pull this off, that's going to be the much more stable structure, and therefore we're going to have a more acidic situation when we pull this off. Obviously, that would mean that either one of these two then would be more likely than pulling off one of the sp3 situations that we would have if we had the single bonds. Okay, remember single bonds are going to be longer, and therefore when we leave that there, that's going to be a less stable situation. Remember that for each of our cases, that what really, really matters here is stabilization. How are we stabilizing things? Okay, are we making it more likely that that negative charge that's going to get left, and that is pretty much always the result here when our proton leaves, our acidic hydrogen leaves, that that electron pair comes back into the fold, that is going to become a negative there. And so what sort of situation is going to make that more stable? Okay, a more electronegative element would do it, a bigger atom would do it, the ability to delocalize that in resonance will do it. It makes it more stable or easier to pull off if the electronegativity is pulling it away. And then the orbitals, if we've got if we've got the smaller length there, if we've got a greater area of electron density there, then it's going to more stabilize those electrons and make that more likely. So remember that ARIO, that acronym, is going to help you to figure out situations where you're trying to determine it quantitatively, although of course qualitatively. There are, of course, we would much prefer to do it quantitatively, but that just isn't always possible. And of course, there are exceptions to that. We'll run across a few of those this year. But in general, this will serve you well in trying to qualitatively determine the acidity of organic compounds. All right? Thanks, kiddos.